This is a remote pilot aircraft system, or RPAS. It's a fixed wing. It's got 1.8 meters wingspan, and it's one of the common fixed wing RPAS or drones or unmanned aerial vehicles that could be used by people. But before we go into seeing how the moments can be used and how they are useful and stuff, let's just have a look at some of the platform or vehicle dynamics in terms of how it moves around. Okay, so the first thing we need to look at is pitch. Pitch is the motion of the nose of the aeroplane going upwards and downwards. Okay, and note that pitch is controlled by the elevators, which you see on the tail. So moving upwards and downwards. And then we have got yaw, which is a motion towards the left and towards the right. Okay, and yaw is controlled by the tail, with the rudder. And the rudder will move to the left and right, and that will change the yaw of the airplane. And then we've got what's known as roll. And roll is a motion towards the left and towards the right. And the roll motion is performed by the ailerons, which are on the main wing, and they're able to move upwards and downwards. Okay, so now that we've got the three basic motions in place, you just see how it works. So with the ailerons, when a roll has to happen, the one aileron will move upwards, the other aileron will move downwards. Okay, so in this case, if this aileron had to move upwards, and this one had to move downwards, what's going to happen is the wind's going to hit against this aileron, and using Newton's third law, it's going to essentially push down this wing, yet the wind will be coming, or the airflow will be coming at the bottom of the wing. It will hit this aileron at the bottom because it's facing downwards, and that will cause this wing to push upwards. Okay, so that is how your roll motion is able to happen. Your motion happens with the tail. So how this rudder works is that, let's say it moves towards you, then the air is going to flow, it's going to hit this rudder, and it's going to push the back towards the left, which is going to cause the airplane to yaw towards the right. So the tail or the rudder is able to control the yaw motion of the airplane. The same thing as if you had to move the rudder to the opposite direction. It will cause the wind to come past, it will hit against the rudder that is facing towards me. It will push the tail towards the right, which will cause the nose to go towards the left, and so it will yaw towards the left. And then finally, you've got the elevators that are at the back. And they often operate in a very similar fashion. So what would happen if they were moved or in an upwards position like that? The airflow would come past, it will hit those elevators, and it will, because they're lifting up a little bit, it will cause the tail to go downwards. And as the tail goes downwards, it means that the nose will be pushing upwards. And again, vice versa. If the elevators were pointing downwards, the airflow will come underneath the wing, it will hit those rudders, those elevator control surfaces, it will push the tail upwards, and therefore the nose will pitch downwards. Okay, so the center of gravity of such an aircraft is important, and it's generally that it is designed to have a center of gravity at least at the center of the wings. And as a matter of fact, if I take my fingers and I hold here in the center of the wings and I lift up, you will see that the aircraft is balanced. So it won't be tipping forwards or backwards, it is balanced underneath the wings. And so you generally want to have the payload, or most of the weight, as much to the front as possible. The reason being is that if you've got a control surface like your elevator that's got to move upwards and downwards, if the center of gravity was towards the back, because of the arm length being so short then, and therefore also the moment being so short, will cause that the amount of force the pilot has to put on the control stick to move these elevators up and down will be a lot, and will be very difficult to make the aircraft to pitch upwards and downwards. Yet if you can have the weight towards the front of the aircraft, like you'll often find the engines are in the front of the aircraft, a lot of the luggage or people might be sitting towards the front of the aircraft, then that will cause it to have a longer arm length, and therefore there would be a larger moment. So there's less input that the pilot would have to give to control these surfaces. Right, so as a manned aircraft pilot, as well as a remote pilot, and also a remote pilot or RPAS instructor, with those ratings we often have to do these weight and balances on small aircraft such as this, as well as a manned aircraft. And if any of those calculations for the mass and balance should be a little bit out of a certain window, then we've actually won't be able to fly. Might be able to take off, but there might be problems when you want to land. Or you might not be able to take off because the weight distribution within the aircraft could be incorrect. So weight and balance is very important for pilots, and they've got the responsibility of the aircraft and of the flight and of the passengers on board. And so for safety reasons, they've got to make sure that all the things are inspected around the aircraft, as well as making sure that the weight and balance of the aircraft is satisfactory for safe flying. Let's have a look at the mass and balance of the Sling 2 aircraft. So this is a typical form that the pilot would have to complete. Okay, so the formulas are essentially shown over here that would for completing different fields. Okay, so initially the pilot would have to indicate how many liters are available in the aircraft. So in other words, this will be in liters. The maximum is usually for the Sling 2 at least is 150 liters. And then the that value would then be taken and multiplied by 0.72 to be able to get the actual weight of your fuel. Keep in mind that fuel has a density that is less than water, and so it will be therefore a value that would be less than 1 for the density, so therefore it's 0.72 has got to be multiplied with. Okay, so the aircraft has a known empty weight of 397.4 kilograms, and then you've got the option to be able to say what the right seat person's weight is, the left seat person's weight is, the baggage in the front and the baggage in the rear. So these weights can be then placed in over there. It's important to also keep in mind that there are mass limits. So for example, the front baggage can't be more than 35 kgs and the rear baggage can't be more than 25 kgs. Same time, the fuel cannot be more than 8 kgs. So even though we've got a maximum weight of or maximum amount of 150 liters of fuel that can go into the aircraft, there is a limit in terms of how much weight that fuel can occupy. And then we've got a takeoff mass. It's also got a limit of 700 kgs over there. Okay, so your takeoff mass is then essentially adding up all these weights together, and you've got to always also include the empty value over there of 397.4 to get that sum over there. And then the moments have to be calculated. So this specific weight or force that we've got over here is multiplied by the arm length to get the moment. Okay, so for example 397.4 multiplied by 1671 is equal to 664216. And so each weight over here is multiplied by the arm length to get your moment, and that's done for all of them over here. Finally, once you've done it for all of them, you're able to add all these moments together to get the sum of the moments over there. And then the arm can be calculated by taking this moment value and dividing it by the total mass to get your total arm length over there. Okay, so then there's your percentage Mach empty that has to be calculated. So percentage Mach stands for mean aerodynamic chord. Okay, so the percentage Mach when it's empty is calculated. So essentially this is taking the sum of the moments, but all of those with the stars next to it. So if your fuel tank is going to be empty, obviously you're not going to have any fuel over there, so this value over here will be 0. Okay, so you're basically going to add all of these moment values together. Remember to also include the moment value calculated there for the empty aircraft. You're going to divide it by the sum of the weight, which is the sum of the weight of that you've entered in over here in this column. But keep in mind fuel is 0, so therefore we won't have we won't be adding up the fuel value over there. Minus 1366, and then all of that in brackets multiplied by 100 and divided by 1339. Okay, and then the mass of it being empty is, again, we're just adding up all these values except for the values of the fuel, and we'll place the value over there. The percentage Mach, and again Mach is mean aerodynamic chord. So the percentage Mach at takeoff is going to be your takeoff arm, which will be this value over here that we've calculated, minus 1366, and then we're going to take that answer, multiply it by 100 and divide by 1339. Again, the mass takeoff is going to be essentially all these weights that we've calculated over here, and it's going to be the takeoff mass over there that we've already calculated, which will be entered in over there. And then once we've done that, then we can plot this percentage Mach empty and the mass empty as XY coordinates on this specific graph, and we're also able to then look at the percentage Mach at takeoff and the mass at takeoff and plot in this specific graph. And we've got to make sure that the empty and takeoff percentage Mach is within this envelope or within this specific rectangular shape, and if it is, it's safe then to take off or land. If it's not, then it will be unsafe, and then we've got to re-look at getting lighter passengers, maybe decreasing the luggage, maybe decreasing the fuel even. So it all depends on what it is, and we have to adapt the masses in the aircraft to be able to accommodate it so that these values will be plotted within this rectangular space. It's best showed by using an example. Okay, so here we've got a clear mass and balance sheet, and we're going to complete it. So in this specific example, we're going to assume that we've got 50 liters of fuel. So we'll place 50 over there. And 50 multiplied by 0.72 is going to give us the mass of the fuel, which will be then equal to 36. Okay, now let's say in the right hand seat you're told that there's a person sitting over there of 110 kgs, and on the left hand seat there's a person sitting over there that's weighing 100 kgs. You're told that in the front baggage or luggage it's got a total weight of 10 kgs, and then we've got the rear baggage which has got a total weight of 25 kgs. Okay, so up to this point these values are correlating over here with the mass limits. It is within those limits, so we know it's safe to look at least to use them. Okay, so we can add up all these values together, and adding up all these values together we get a total of 678.4 kgs. Okay, now that we've done that, we're going to multiply each of these weights with its correlating arm value to get the moment. So 110 multiplied by 1959 is equal to 215,490. 100 multiplied by 1959 is equal to 195900. 10 multiplied by 2508 is equal to 25080. Then we've got the rear luggage, which is 25, multiply that by 2896, and we get 72400. And then we're going to say 36 multiplied by 1511, and we're going to be getting a value of 54396. Okay, now that we've done that, we're going to add all of these values together. So 664216 plus 215490 plus this value, that value, that value, and that value. Adding them all together, we're going to get a value of 1227482. Okay. Now we're going to take this value that we've just calculated and we're going to divide it by 678.4, and that will give us our arm length. So that is equal to 1809.3779. Okay. Common mistake is that people think that they need to add all these arm lengths together to get this value, but it's not. It's this moment over here, divide by the takeoff mass, and you get this arm value over there. Okay, now that we've done that, now we need to calculate the percentage Mach when it's empty. So we're going to be taking the sum of these values over here with the asterisks next to them. We're going to divide them by the sum of the weight over here. So remember, the empty value of the aircraft weight we're going to take into account as well, except for the fuel weight over here. So we can't go and take this final takeoff mass value, it won't work. So it's going to be 397.4 plus 110 plus 100 plus 10 plus 25. Okay, and then once we've calculated that, we're going to subtract 1366. We get an answer, multiplied by 100 and divide by 1339. And we will get an answer of 34.36. And then we'll also be looking at what is the mass when it's empty. So remember, that is going to be all the values over here except for the weight of the fuel. So 397.4 plus 110 plus 100 plus 10 plus 25, and that's going to give us an answer of 642.4. Okay, now that we've done that, let's look at what the percentage Mach for takeoff is. Okay, so essentially we're going to take the takeoff arm, which we've calculated over here as 1809.3779. We're going to subtract 1366. We're going to get the answer for that, multiplied by 100 and divide by 1339. And we will get an answer of 33.11. Okay, and then what's the mass at takeoff? Well, that is already calculated over there in this field. It's 678.4 because we've taken into account all the weights over here, adding up together, so we can place that value over there. That's 678.4. Okay, so that's the same as our takeoff mass that we've calculated over there already. Okay, now that we've got these values, we've got to now plot it. Okay, so first we're going to be looking at for empty. So percentage Mach at empty is 34.36. Okay, so if we look at our graph over here, 34 is located over there, 0.36, so it's going to be a little bit over that. Okay, so we know it's going to be over here somewhere. And if you can see the faint line over there, it will be just to the right of that faint line. The mass at empty is 642.4. So if we look at the aircraft mass over here, it's 642.4. So that's going to be very close to 650 over there. So it's just going to be below 650. So we can bring that across over there. So we can make a mark over there. That's going to be our percentage Mach empty. Okay. Then we're going to be looking at the percentage Mach at takeoff. Okay, so we've got here 33.11. Okay, so 33 is between 32 and 34 over there. So it's just past that, so it's going to be somewhere located over here. And we've got a mass takeoff of 678.4. Okay, so 678.4. So that's going to be between 650 and 700 over there. Okay, and so for that we're going to find it will be located roughly over there. Okay, so that's going to be our percentage Mach takeoff. Okay, so now we've plotted both of those points that we've got over here using those values for our X and Y's axes respectively. Now, is it safe to take off with this aircraft? And the answer would be no, because both the percentage Mach at empty is outside of this envelope or this rectangular box, and our percentage Mach at takeoff is outside of this rectangular box. So for both cases, for takeoff and for landing, with landing you're going to be assuming that you might have a complete empty fuel tank. It will be unsafe to perform with this specific configuration. So it won't be safe, and therefore if a person would want to still fly with this aircraft, they would have to reconsider, relooking at the values of the luggage, maybe get lighter people to sit in the seats over there, maybe use less fuel over there, and they would have to play around with these numbers until they get both of these points within this rectangular shape. And if once that's happened, then they can sort of say, okay, now they can take off and have a safe flight. This is a Sling 2 aircraft. It's able to take 2 people, the pilot as well as a passenger. We're going to be looking at some of the features that's involved with it. The pre-flight inspection is needed to be done. The reason why you want to do a pre-flight inspection is that you can't just go while you're in the air, pull over to the side, and if something goes wrong, and then fix it. So you need to make sure everything is in working order, very much the same way as you would do with a car, and or at least that's the way that you're supposed to be doing it. So we're going to be looking at the pre-flight inspection things, and then just look at a few important aspects that are related to the instrumentation within the aircraft itself. Okay, let's start over here with the engine and start doing inspections. We open up the engine compartment. This is a 4-stroke engine, carbureted engine, and what we do is we try and sort of see if there's anything that might be inside of it, like an animal that built a nest maybe, or that had babies or so during the night. This often happens especially with cats or rodents. Make sure that there's no cables that have been chewed off. Click and then close the engine compartment. We then move across, and we're going to be looking at the prop, the propellers, what is going to be letting the airflow and pull the aircraft. So we need to make sure it's all good, all the blades are looking good, inspect them. It appears to be all in order. We then come across, have a look at the front wheel. Make sure that they're straight on the front wheel, and make sure that all the bolts are over there in place and all the nuts are in place. We don't want to have a situation where we're busy taking off and the wheel falls off. We then come up to the other side of the engine compartment. Okay, and over here what we want to do is all the fluids are located over here. So we look at there needs to be certain fuel fluids inside of it. As you can see over there, we've got our brake fluids, and they've got minimum readings that it's got to be at. We've also got our normal oil over here, which we're able to open up. And we're able to also have a look at the indicator over here. So the wheel's got like a flat section here on the dipstick that you'll see, and that oil must be within that flat section over there. So that's a good indication to us that there's enough oil within the engine. Right, so we can close the engine compartment again. And then we come and have a look. Over here we've got air inlet, which will go to the air vent which is inside of the aircraft. We will then also check to make sure that the leading edge of the wing over here is in good order, nothing set it and impacted and damaged it. What we will also do is check the fuel to make sure it's filled up with fuel. As you can see over there, it is filled up with fuel, and it's got a greenish color as well, so we know that is all correct. As you can see, 75 liters on each side of each tank in each wing. Can either be avgas or mogas. That's quite nice thing about the Sling 2s, while the other aircraft sometimes are restricted to having only mogas or only avgas. We then have to look at the ailerons. So these are the ailerons that make the aircraft roll to the left and to the right. And we've got to make sure that all the nuts are in place and all the bolts are in place. We don't want to lose control of the aircraft if these are missing. Also, when it comes to the flaps, we will be looking at those nuts and bolts as well. So the flaps are secure. You can pull onto it, and the flaps essentially creates a drag on the aircraft. So when we bring the flaps down to different stages, it will create a drag, allow the aircraft to go slower. Okay, and then again over here we will just make sure that the nuts and bolts are in place. We come across to the tailpiece. This is the elevator. The elevator moves up and down. That controls the pitch of the aircraft. And again, we're going to just check to make sure that the bolts and nuts are in place. As you can see over there, that bolt and nut is in place over there, as well as over there. Coming down back to the rudder. Remember, the rudder's point of view is that it controls the yawing of the aircraft. So that's the tail piece over here, and that's controlled by these cables. So we make sure that the cables are secure and that it's able to operate properly. Coming back to the elevator over here, as you will see that there is this extra little piece over here, and this is known as a trim tab. And essentially what it does is it just helps to adjust slight deviation through the rudder, in the elevator. The reason for this is it helps with the control. So if you find that the aircraft is pitching up a bit too high or a bit too low and you're ascending or descending while the aircraft is supposed to continue straight and level, you're able to adjust this, and this little control surface is able to correct that adjustment, and helps you to be able to fly the aircraft with less pressure on the control stick. Again, we're just checking these nuts and bolts over there. They will in place. There we go. We then come across. We do the same check over here in terms of the this specific flap. We go across, check over here, the nut over the bolt over there, and the bolt over, and it's all secure over there. The paintings help us to see that there's been nothing moving. We have to also come in there, have a look at the bottom and make sure that all the nuts and bolts are in place over there for the flaps, so that we don't lose it. Okay, so we can see that all over there. We're back at the aileron over here. Again, over here we're able to check the nuts and bolts, and the aileron is able to move very freely, which is important. Okay, so we've got our nuts and bolts over there. Okay, then we come here to the Venturi tube. We've got to have a look at the inside of the Venturi tube, make sure that there's nothing inside of it. You could have an insect that created a nest over there like a wasp. And the purpose of the Venturi tube is to detect this airspeed. So essentially it's the airflow going into this tube. It's a pressure sensor that you've got over there, and depending on the amount of air that's flowing into it, because the aircraft is moving forward, we'll be able to tell you what the airspeed is, and that just detects in terms of the air pressure. Coming across over here again, we're able to look at the fuel. And as you can see, it's filled up with fuel. So with one full tank with both tanks being filled up, it allows us with about 8 hours of flying time, which is quite good compared to other aircraft. Okay, then coming down again, we're just checking the back wheel, two back wheels. The thread is looking good. We can see that all the bolts over there. Coming across this way, you can see all the bolts are in position over there, so that looks all good. And we've also got to check the other wheel. And to check to make sure that all the bolts are secured. The thread is fine. And over there, the bolts are secured. Fixed-wing aircraft or aeroplanes have got tanks for the fuel within the wings, and there's what's known as a fuel staining point over here at the bottom. So what's going to happen is that you want to check make sure there's no water inside of the tanks, because that could be a problem if you're flying and suddenly there's water coming into the tanks. So to be able to check it, we've got a fuel strainer that we're able to stick here in the bottom. We're able to strain some fuel out of it, and this is specifically MoGas or petrol. So this is the color of the petrol that you can see over there. Other aircraft will be able to use what's known as F-gas or aviation gas, and it's just got a different octane compared to the MoGas. MoGas stands for motor gas. And so essentially what we do is we look at the strainer and we try and sort of see at the bottom over there, is there any water that we can see over there? If there's any water density is heavier compared to the fuel, so it would code to the bottom. So these access points that we've got where we strain fuel, that's usually at the bottom of the wing, lowest point where the water would then accumulate, and we'll be able to detect if there's any water with inside the fuel tanks. Okay, so this is the cockpit of the Sling 2. As you can see, there's two seats over here. The left hand side seat has always got the pilot in command that will be sitting over there. The passenger is always on the right hand side of the aircraft. And these are the different instruments and controls that you will see inside the Sling 2, and we will have a look at this in greater detail. Okay, so before we go on a flight, there's obviously some of the instruments we need to check. We need to calibrate them, make sure that they're all in working condition. And so what I'm going to do is I'm going to be going through some of the instruments that get often used, that you often will see in the cockpit. Okay, so firstly let's have a look. How's the rudder's controlled in terms of the yaw in motion to the left and the right? That's done with these pedals over here, so we're able to control them by pushing them in and out. We're able to then control the motion of these pedals, and we can then have the airplane yaw to the left and to the right. This is our control stick, or the yoke. It allows us to pitch up and down, and this is obviously done with the elevator. We're able to move with the ailerons to the left and to the right. As a matter of fact, if you look out over there, you will see the ailerons moving to the left and to the right. So as it moves up and down over there, it actually then allows for the aircraft to roll to the left and to the right. Okay, then coming in over here, we've got our master switch control over there, which gives power. We've got the switch key over here for the mags, left and right mags, as well to start the engine. And this is essentially the cockpit that you would usually see in the Sling 2. As you can see, there's quite a few instruments over here. I'll go very briefly through them so that you can see what they're all about. This is an electronic system. I'm not going to go through that now, I'll go through it later. But let's just have a look at some of the analog instruments that there are. So essentially we've got the radio system over here, that's the avionics, that allows us to talk to air traffic control. We've got over here our airspeed, which is in knots, and that's so this airspeed indicator tells us what speed the aircraft is going in the air. It's not necessarily the ground speed, so if we've got a huge high headwind coming from the front, it will slow down the aircraft, and therefore that speed that we're actually traveling at in relation to the ground is not necessarily the same as the airspeed. Alright, then we've got the altimeter over here. It tells us height above the ground. This is in terms of how many feet we're off the ground. You'll see that there's small numbers over here. That is also known as the Q and H setting that we have to do. So over here it varies, and that's essentially our air pressure. So essentially what happens is that the altimeter uses a pressure sensor to determine how high the aircraft is above sea level. But the issue that we've got is that the sea level can change, or the initial height can change, and this is mainly because of the reason that if we are, for example, having a cold front that's coming through, this cold front can actually cause like a low pressure to come across the country, which obviously is going to have an effect on the air pressure, and that could indicate to us that we might be in a higher altitude compared to what the aircraft actually is. So we need to calibrate this, and as we calibrate, you'll see over there we should be on ground level now at the moment. It just leaves us off over there, so we can turn that lever and it'll be on a 0 position over there. So as we turn this, that altitude meter at sea level will change, which is your QNH. And you'll see that this is something we get the information from air traffic control. When we go for the flight, we verify what it is, we change it over here, and then we are able to know exactly how high we are. Right, we've got some fuses over here. We're able to control the flaps over there with different stages. We've got different switches over here for the different things that get switched on. We've got our fuel indicator, at least a fuel switch, so we can switch between the left hand or the right hand side tanks over there. We've got our brakes lever that's over here. This is our fuel throttle. Okay, so this is essentially the manual system, and even though it is very basic, the electronic system gives us a lot more information. We can often have to rely on these specific gauges, and at least they give us information that we're able to then successfully fly the aircraft in a safe manner. Okay, coming across over here to the control system, the electronic control system. So a very sophisticated system. It is allowing us to show us quite a lot of information. For example, we know what Virginia Tower's frequency is over there. We're able to see all the details in terms of which aircraft it is. We've got over here on the right hand side information in terms of engines, RPM, for example. There's revolutions per minute of the engine. We're able to see what the oil pressure is, the oil temperature is. We're able to look at what the fuel quantity is at the bottom as well. You can see we're in green, not completely full tank, but we're relatively full tank over there. We're able to sort of see also here with the compass where we're going. And over here, this is obviously seen as in a digital manner with the GPS. We're able to see how many degrees we are. Yet there's also this manual system over here. As you can see over there, we've got still compass showing to us that we are at 210 degrees facing at the moment, which is relatively correlating to the 212 degrees that we've got over there. Over here we've got our artificial horizon, and our artificial horizon is showing us how the aircraft is pitching forward, how it's moving to the left and to the right. We're able to also see our airspeed over here, and we're able to also see in terms of the elevation. We're able to sort of see if we're able to have flying in terms of increasing the height above the sea level or decreasing. You also see over there we've got the 1017 millibars. That's a QNH set for this specific system at the moment. Even though we changed it on the analog system, it still needs to be changed on the digital system. So you'll see we'll do that as well. This electronic system has also got quite a sophisticated GPS system involved. So we can able to go to different points. We're able to sort of see what's happening over there, see what the degrees is, the GPS degrees are over there. So that's quite useful for us to be able to use this in the aeroplane, especially when flying, when navigating. You're able to know where you are and how to go to different directions, which maybe you're looking for different airfields, maybe you're looking for different places, and you're able to put it in over here and it's able to guide you accordingly. It might appear that I'm in an actual aircraft over here, but this is actually an advanced simulator. It is quite sophisticated that it's got the airport, Virginia airport specifically, loaded onto it, and as you can see in the background, you'll be able to see the field. You can see different buildings. So it's actually amazing in terms of the feeling that you've got while sitting over here. It actually feels like a real aircraft. The instruments that are inside the simulator is very much the same as what you would find in an aircraft, and we'll just go through some of those again and just sort of see how the different effects have got on it. It looks a little bit different to the Sling 2 that we had to look at, but at least this is also in terms of, as for this specific aircraft, it's got two engines on the wings, or one engine on each wing. and so it gives you that twin engine effect that you also will experience in the actual aircraft. These simulators are actually so sophisticated that many pilots that are flying commercially for specific airlines will do all their training within these simulators, and when they actually go flying with passengers inside the aircraft, that'll be the first time that they would actually be inside the physical aircraft and actually flying it. So these simulators are able to allow them to train quite well and to be able to be familiar with the different instruments, as well as how to control the specific aircraft. Okay, this is a view of the simulator from behind the seats, and it's all been controlled by these, or at least by this computer over here. So these monitors are able to allow you to change the settings. We're able to change the area that we're taking off from. So over here would be specifically for Virginia Airport, and all these different settings and controls can be configured. You can also initiate different scenarios, like there might be bad weather, there might be engine failures, and by initiating these type of scenarios, the pilot will be able to counteract and prevent any failures to happen and any accidents to happen, and will be able to fly the aircraft and see if they trained enough to be able to do what's needed. Okay, so having a look at the pedals over here at the bottom, to control the rudder for the yaw to the left and to the right. So we've got the same type of effect over there. We've got the brake pedals at the front, which this specific aircraft, or at least simulator, has got. This is the yoke, which allows us to change the pitch of the aircraft as we move it up and down, and we're able to turn it left and right. And it's quite advanced. The simulator, if you look out towards the wing, you'll be able to sort of see as well how the wings, at least the ailerons, are able to go up and down as you're actually busy turning the yoke to the left and to the right. Okay, so again, got pretty much the same instruments over here. We've got the airspeed, which does the airspeed of the aircraft in knots. We've got our horizon, which allows us to indicate whether the aircraft is pitching up or down, or to the left or to the right. At the moment, it is appearing like we are turning. It's just because the simulator hasn't fully started yet. We've got the altitude, our altimeter over there, again to give us the altitude that we're above sea level, and that would be in feet. We've got our vertical speed indicator. So if we are increasing in altitude or decreasing in altitude, we'll be able to see that over there. And this is also our compass, and obviously this specific compass, at the moment it's appearing to be around about just under 210 degrees, which we saw in the Sling 2. So it gives us an indication of direction to be going. Over there's the digital output as well, which gives us of 143 degrees. So this specific layout is what you would obviously, or most commonly see in most aircraft, and these are the instruments that you would usually be seeing. That would be the analog instruments, not necessarily in the digital format. And then at least with these basic instruments, you'll be able to do a safe flight when in the air. Okay, then coming down over here, we've got numerous different switches, like the left engine mags that get switched on. We've got the right engine mags that can be switched on over there. We've got different switches over here in terms of the fuel pumps and the carb heat and de-icing that can happen. Even the avionics masters can be switched on over there. Coming across over here, we've got more of a digital screen over here that tells us in terms of oil pressures, we're able to see the temperatures of the engine, and then there's also a few instruments that are identical to the ones that we see here on the left hand side, such as the altimeter, the airspeed, ESR horizontal line over there for the horizon, and then we've got our again a compass indicator over there, trim tabs in terms of the elevator that we're able to trim over there. This specific system's got actually a rudder that can be trimmed as well, so it's not just over an elevator, but it's also the rudder that can be trimmed. And then we're able to see the fuel gauges over here simulated. You can come down over here, and we've got our radio system as well. We've got our throttle, which looks a little bit different, but it's compared to the Sling 2, but this is the throttle is over there. We can also adjust settings to the mixture and the propeller, and then there's different items like the park brake that is also common, as well as your pitch trim over here. This is something that we would be doing, or at least in the Sling 2, would be done on the controls itself with the button that we go up and down, but this is done with the wheel that is able to be turned. So as you can see, the setup is very much the same. As we have a look to the outside, it looks very much the same as we would experience within the aircraft. You can see the propeller over there. We're able to again see the ailerons going up and down over there as we turn to the left and to the right, and then again coming across to the left hand side of the aircraft, we can also see how those ailerons change. So in this type of system, we are able to get quite familiar with the instruments, and we are able to train accordingly for safe flights to happen. We're going to be going on a flight, and just to see how the different instruments are being used while flying the Sling 2. So firstly, we do our pre-takeoff checks. We're going to make sure that all the instruments are operational, the fuel's all working, the engine's temperatures and pressures are all in place, and then that's why the engine is running, and then after that we are able to then pursue with a flight. Virginia Tower, Zulu Uniform Sierra Tango Foxtrot, good day.
Zulu Uniform Sierra Tango Foxtrot, Virginia Tower, good day.
Virginia Tower, Sierra Tango Foxtrot has 2 souls on board, 5 hours fuel endurance, and will be heading towards the general flying area, requesting taxi instructions.
QNH 1016, runway 23 in use, report at holding point.
QNH 1016, report at holding point 23, Sierra Tango Foxtrot. So over here, I had to change the QNH setting so that would be to indicate what is would be 0 feet on the instrument when it's at sea level. Okay, and then you will notice that everything that the air traffic controller would say, I would have to repeat, and that's to make sure that I've heard the instructions correctly and that I'm able to follow the instructions that they need me to follow. Runways are numbered with 2 numbers, so in this case it's 23. That would stand for it going in a direction of 230 degrees. And in the opposite direction will be 180 degrees from that. So in this case, 230 degrees minus 180 degrees would give you 50 degrees, and that would be for runway 05. So it's always looking at the other, at least at the first 2 numbers of the runway. So we've been cleared to take off. We check the engine's temperatures and pressures again, and then we make sure that everything is still correct, and that there's no overheating happening before we take off. We'll be rotating at 55 knots, so that is the speed that we'll be going on the runway. Once we are we've taken off, the best climb rate will be at a velocity of 75 knots. In the event that we're still on the runway and there should be an incident that happens with the engine, we just reduce the power and vacate the runway. But after we've taken off, we will then have to perform emergency landing. And this we can do on a beach along the coast over there. And the best glide speed for these things, Sling 2 aircraft, is 72 knots. So as we're going, you'll be able to see the Moses Madiba Stadium. It will be appearing towards the right very soon. And this is a famous landmark in Durban, South Africa. Okay, so we're busy going southbound from the harbour entrance. At the moment we're flying at 1,000 feet in altitude. So in aviation, all your horizontal heights are always in feet, while your distances away that you might be, that will be in terms of vertical distances. So that would be from one point to another would be in meters. We always have to repeat and notify other aircraft of our location. We're above, so or a beam of a certain point. And we've got to always give our intentions of where we're going and what height we are at. So here we're going to be doing a flight through a cloud, just to demonstrate how important it is to use instrumentations. And as you can see, as we're going through this cloud, you're starting to see less visibility, you can't see the horizon, and you need to rely on your instruments to know what orientation you are in terms of the pitch of the aircraft, the roll of the aircraft, and the yaw of the aircraft. And if you don't have this, it could cause major issues. I'm reducing the power over here for a lower RPM. The aircraft has a frequency that will cause more vibration, and you will notice with the ultimate needle vibrating. And so it's important for instrumentation be considering damping. Damping happens with the video camera, for example, and the human body will absorb any vibration to prevent the recorder to be jumping around. So different air speeds are measured over here in knots, and we have to at least observe it over there, as well as a altimeter, and we're able to compare it with the Garmin, which is obviously digital. And in the other instruments would be obviously the analog instruments. People think that Garmins are very accurate. They are more accurate than the analog often, but they're not always that accurate. And an example is at the Greenwich Prime Meridian. So this is where there's a separation between the east and the west in the world. People often go there. So over here I'm standing on both in the east and in the west of the world. And as you can see over here, it's not that your satellite or GPS system is broken. There's a difference between the GPS and where the meridian is. And it is due to the fact because of this being distance away, and I actually went to the point where it was exactly 0 on the GPS. And when I visited the Greenwich Meridian line, and it's a situation that a GPS is considered to be accurate because it's got the atomic clock that's on the satellites. And calibration is still needed. And I've even experienced this on a bicycle with my Garmin. At certain segments, you start off, and after 2 years, it's been 20 meters further. Garmin has even claimed that I have not even finished a cycle race before, even though I've given them all the evidence in the past and shown them that I have completed the race. According to the Garmin device, it's indicated I haven't actually cycled exactly that distance, and it's out with a few 100 meters. So these are always things one's got to consider when doing calibrations and of systems. Okay, so I'm going to be doing some examples. I'm showing you different air speeds. So you will see over here with the analog system, it will show you we're going about 105 knots. While on a digital system, you will see that we're going at around about 100 knots. So there's a difference that we are able to see over there. You also will notice that with the vertical speed indicator, there would be a bit of a delay, which one needs to take into account while flying. So while I'm busy going here over the same RPM or engine speed, I'm busy making an 80 degrees turn, and you will notice that initially the speed is 92 knots, and then it will eventually be increasing to 110 knots. And this just depends on whether we've got a headwind or tailwind. At 92 knots it would be a tailwind, headwind would have been at 110 knots. And obviously the ground speed will be less when you're going in the headwind direction. So over here we're busy flying towards Mars, and you'll be able to see the Sappi paper factory that can be seen there on the right hand side. You can see the smoke and the water vapor coming out from the factory over there. A good indication always to know in terms of which way the wind is also blowing if you need to do emergency landing. So we'll be turning back to Virginia Airport now. We've been cleared to land by the air traffic controller, and we're in our final approach on runway 23. We keep on monitoring the instruments to make sure that we don't go too slow, because we don't want to stall the aircraft, because that can cause that we can crash. And stalling is when there's not any airflow going over the wings, and therefore keeping us at least in the air. So you must have a look at the videos in the description and the links of videos that I will be giving over there, which allow you to have a look at the 360-degree camera within the cockpit, and that would be something that you could have a look and see how it looks at different angles within the cockpit as we were flying. As we get to the end of the flight, we have to reset our configurations in the aircraft. And then we have to follow different instructions as well in terms of complete switching off of the different instrumentations, the avionics, and the engine to make sure that everything is done in a certain procedure, because we can blow certain instruments if we have, for example, the avionics. If we had to switch off the engine before the switching off the avionics can be damaged.